Hello everyone and welcome back to the course. Today we'll be dealing with the topic of concept drift. You can already read that there are two important words here, the one being concept and the other one drift, and now you might wonder what do both of these mean and what is their combination about and what does all of that have to do with machine learning in specific and AI in general. But before we dive in, let's have a short repetition on the last lecture. So in the last lecture, we talked a lot about the training of your final model. So you learned that the model training and testing comes before the operational deployment, right? And this also involves the typical fine-tuning. But then in the end, when it's about deploying the model, your most important goal is to build the best model possible and not anymore to estimate the performance on unseen data. The second thing that we discussed is the different AI autonomy levels that you can have, deciding on whether AI is able to take action. This goes back into our initial definition of the agent-oriented view, right? An agent having sensors and actuators, but the cases that we discussed, there were also some where the actor only has sensors. We talked about the challenges that you typically have when it comes to machine learning deployment. So different programming languages, why is it important to use things like GPUs? How do you manage unpredictable costs, for example, with a serverless architecture, and so on. And speaking of serverless architecture, this was one of the options that we discussed when it comes to the deployment options, where we have typical monolithic solutions, microservices, and various options at hand. And I also told you that there are nowadays large platforms that help you in the not only training and testing the model, but also help you in deploying those models on large scale, right? Solutions from Amazon, Kubernetes, Cloud Foundry, and other machine learning as a service solutions. And then finally, I introduced to you the idea of ML ops, right? This paradigm that combines development operations together with machine learning and tells you how do you deal with operationalizing machine learning, deployment, and development. And the interesting thing is that today we'll dive actually deeper into why ML ops is such an important paradigm. If you recall the general story of our lecture, this also means that today we're in this last bit of the typical AI lifecycle where we look at AI as one isolated entity, and this is also going to be the last lecture before we then move into AI within systems. So while the last lecture was all about training this final model and deploying it, now the lecture of concept drift deals with how do you ensure the validity of your model over time when there are changes in your environment. And speaking of environment, this also brings us back to this framework of our intelligent agent. And now we look at this top bit here, right? At the sensors that continuously read data from the environment, and how do we deal with changes there when it comes to the design of our agent. So we have multiple objectives at hand that we want to look at today. First, I want you to explore the term concept drift. So what does it mean? What is a concept? What is a drifting concept? So that we have the foundations set. Next, I want you to understand the importance of continuously monitoring your deployed solutions, and of course to detect those concept drifts. I then want to go deeper into the different possibilities that you have when it comes to the drift detection. And then finally, how can you adapt your prediction models to address those changes in the environment. Nice. So for the remainder of today, I will give you now a short introduction on why is this an issue at all? Why do we talk about it? Why is it problematic? Then I want to go deeper into the theoretical foundations of concept drifts and how we can adapt. I want to give you two deep dives on precise algorithms that are used for concept drift detection. And then finally, let's have a look at a few real world examples. Now, we stopped the last lecture with this definition on microservices and how we deploy our solution as a reusable, you could say, atomic service that gets called upon and then outputs recommendations. The question that we want to dive deeper into now is, how do we keep these machine learning microservices correct? And why is that an issue? Well, let's imagine a factory plant, right? Let's say it's a brand new factory plant and we have sensors built in there, right? State of the art, very advanced. We read out from this environment via the sensors all the time, which also means that we build our entire ML setup in that environment, right? So this was used as a training and as a test environment. This means our machine learning model is based on this training environment, which is also truthful in this case, because that's where we originally built it. And this will also lead then to the deployed machine learning model. Again, on how we do that, we covered this last time. Now, unfortunately, in the real world, things change. So your productive environment gives you a continuous stream to this deployed machine learning model. And this machine learning model will keep on making predictions, right, with the data from this productive environment. So we have a continuous data stream from there to the deployed machine learning model. It will make predictions on, for example, when will a part in this factory be within quality or out of quality. But what we don't account for, at least yet, is that you have changing context and then even changing data over time. Right? One thing is that the sensor might wear out over time. That's very typical, right? Not all sensors are digital. You have these drifts in analogous sensors, which are very common. But it's not only that, it's also that we're doing predictions to make things better. That's why we approach this in many cases in the first place. And these predictions can lead to actions. So based on what the deployed model recommended or predicted, we might have made changes in our environment. And due to that fact, the productive environment might differ from the training test environment that you originally had, right? So you have multiple factors which will lead to a different productive environment, here depicted in blue. So there's a difference between the productive environment now and the one that we originally used for various reasons. And this leads to different data distribution. And obviously, as sensors wear out, as we receive different sensor measurements, or as they rust, as we change the environment, our model might not work as well anymore because it originally was trained in this scenario above there. And that was one example now with the factory floor, but obviously there are way more examples out there. So, for example, let's take sentiment prediction, very common in social media use. You want to predict the sentiment of a tweet, for example. Is that positive? Is that negative? Is that angry? What type of emotion does it have? And let's say those communication patterns, they will not be the same over time. They will change. People use different languages. I don't mean different languages where then, as in different country, different languages, but within each country, the language changes over time. The topics that are being discussed change over time. You have the introduction of new words, or you have technical decisions like Twitter wants double the amount of characters that are possible, right? So there are different communications patterns, but if you don't update your model, it will still have those patterns in mind from the original form, right? So what does it mean as a result? How well does your model work in those cases? If you look at the prediction of prices, for example, in the energy market, in electricity prices, things might change here. So you can have policy changes, for example, new subsidies for renewable energies, but your model hasn't seen those ever. So what will be the result of that? Or again, the last example, the prediction of downtime, very typical in industrial machine learning. You change machine parameters in an industrial context, hopefully to better something. But what does that mean for your initial model, right? So you see this idea of changing context, changing concepts in data is very, very common and very realistic. So we have to somehow account for that. So how do you account for that? Let's have a look at a very simplistic example over here. let's say you have a faulty product or a good product. In this case, those are the blue dots over here. You have a faulty product, which are the red dots over here, and a good product, which are the blue dots over here. And you try to separate this now with a basic machine learning model, right? So you did your training, your testing, your deployment, and your originally deployed model works pretty well in separating these two, right? Detecting the faulty ones and the good ones. Now, what you need to do, or what you will be doing now to detect this, is a constant monitoring of your data stream. And what you also want to do is you want to somehow detect any changes in here. Typically with a change detection module that is based, for example, on statistical properties. We get into a few options in a minute. And now your system detects a change. Let's say something changes over here. So those this one red dot that you saw earlier here and now has become a blue dot, and vice versa. So you can see that the original line is not accurate anymore. And now your system can decide between two options, between adapting, which is a slightly adaptation of the model based on the new data, or you do an entire retraining, so retrain the model entirely from scratch. These two methods of dealing with a change will come up more frequently as we progress now. But so the obvious thing is, let's say you detected that your originally deployed model is not working anymore. Now you adapt or retrain, and then your new line might separate these two like that, right? And that's the entire idea of concept drift detection and then concept drift handling with adaptation and retraining. So I guess it's obvious why this is an issue in the real world and why we should go deeper into that. Which is why we should look at the theoretical foundations of concept drift and the different adaptation mechanisms that you have at hand. So the term concept drift comes from the field of computer science, and it deals with the changing data, right? I think that's obvious by now. But what is a concept in the first place? The definition of a concept is the common probability of the distribution of x and y, right? And the x, again, are the features here, and the y is your target. And as I think I mentioned frequently right now, in the real world, these concepts are not stable, but they change with time. So your distribution might have looked something like that from the example there before over here. And now down there, you can see that this changes. And the definition of a concept drift is the difference between two time points of this very concept over here, right? So suddenly time becomes important, which is something that we haven't really looked at so far, right? So you can see that in the initial time period, t0, your distribution might have looked something like that of x and y, and then at a different timestamp, it looks differently. You can see that a few of these points moved around. So there is a difference between these two concepts in time, right? And this is very closely related, obviously, to any timely data. So anything that you stream, like social media data, for example, or as I said earlier, energy prices, stock prices, things like that. And of course, learning algorithms have access to data with timestamps prior to t, everything that is historic, right? That's how it works. But again, it needs to be applied to data elements with subsequent timestamps that we're not aware of yet, or that just come in. So we have to somehow deal with that. And this brings us to the different types of concept drift that exist. So again, let's assume that's our original data distribution. Again, good products, faulty products, for example, that's our original data. And you can already see how our model is pretty good at separating these 2 points. Now, what can change over here is the data points that you see change. So a few blue points are now on the top right. You can see more red points on the top left. And now we have to adapt our model, right? We need to make a new decision boundary over here. That's the one that you can see right here. And that's what we call a real concept drift, right? So changes in pyx, but px might stay constant or not in that case. whereas you have a so-called virtual drift, where you have a change of px without actually affecting the distribution of yx. And you see that in both cases, things changed, right? You can see over here, we have a few of those points over here changed over there. But that means our model is still true. And that's a very important distinction when it comes to determining whether you should act upon the drift. Because as you can see, for a real concept drift, also your model needs to be changed, whereas for a virtual drift, yes, the distribution has changed of your x, but still, your original model is still doing a good job at separating these two. So that's why we always have to distinguish between a real concept drift and a virtual concept drift. So let's give an example to make this even more clear. Let's say we have the scenario of online newsstream articles. And in this case, we look at real estate, and you want to classify whether it's relevant or not relevant to one of your clients as a real estate company. So one of your clients is looking for a new apartment. Let's pick that scenario. Now, obviously, to this person, news on city apartments are relevant because this person is looking for a new apartment, and news on holiday homes are not relevant. So let's now distinguish between the two cases of a virtual drift and a real concept drift. In the case of the virtual drift, the editor of the news portal changes that issues these news on new and upcoming real estate. And because the editor changes, a new writing style might be adapted. This person might use new words, and you definitely have changes in the probability of X, so of your feature space. But that doesn't mean that there are any changes for the initial problem statement of your customer, right? He or she is still interested in city apartments, and they remain relevant. Only your feature space changed because now someone else is in charge and is using different words. That's a virtual drift. Now for the real concept drift, let's say the initial scenario is the same, but now the user buys a house or an apartment and now starts looking for a holiday home. Now in this case, the city apartments become irrelevant and the holiday homes are relevant. That is the case for a real concept drift. And we can agree upon the fact that there are changes in data over time. I think that's obvious by now. But the way that the data changes and the way how you deal with it varies. And we distinguish between a few cases here. The first one is a sudden change, right? You can see the data over there. So something changes drastically at one point in time. So let's say, again, you're on the factory floor, you exchange a sensor in an IoT setting, right? Previously, this was the old sensor, and now you have the new sensor. That's a sudden change. The second case are slow changes. So the scenario that we mentioned over time, a sensor picking up rust, slowly degrading, becoming less accurate, right? Those are so-called slow or continuous changes over time in your data. Then you have things like gradual changes. So let's take the example from earlier from the houses, or let's say finance or sports, which means people switch between different interests. So someone might be interested in finance, but later looks at the sports section of the website, but then keeps going back to finance. So these are all these gradual changes, for example, between two topics of interest in a user scenario that is looking at websites or is looking at ads, and so on. And closely related to that are reoccurring concepts. So these are mostly seasonal patterns or sales forecasting. So for example, ice cream sales, sunglasses sales on winter clothing, right, gingerbread, and so on. So reoccurring concepts over time where you have clear seasonal patterns. That typically happens in sales forecasting. And then the final case that is not a concept drift by definition, but should be mentioned here, is of course outliers. Because who tells us if this is an outlier over here, or if this is part of a gradual change, or this is the first part of a sudden change, or this is the first part of a reoccurring concept like a new season? And that's one of the main issues, to be honest, in concept drift detection, is the question on whether we look at an outlier or we look at an actual change in the data. So that's important to note, and hopefully the methods that we talk about today can help in that a little bit. And this brings us to the challenges that you now have when we talk about these deployed machine learning services in the concept drift environments. Because what are the challenges that you're actually up to? What do you need to solve here? First one is detect the drift. So detect the concept drift as soon and as accurate as possible. And once you did that, the second step is obviously adapt the model quickly if needed. Again, distinguish between a virtual drift and a real drift here. But there are, by the way, even cases of a virtual drift where you still might want to adapt the model. Third one I just mentioned is distinguish the drifts from noise. And on the other hand, the challenge is to be robust to noise in the way that you deploy your monitoring and detection solution. Another big challenge is recognize reoccurring contexts like seasons. Right? How do you know what type of drift that is right now? And is that the beginning of a new season, or is that just an outlier, or is there another reason for that? And then the most important one is operate in less than example arrival time. So if you're lagging behind in detecting your concept drift, let's say you're lagging behind 3 months, then the new season already starts, right? And then you don't have enough time to adapt. So it is absolutely important in the real world to operate quickly, right? This is, I think, a meaningful combination with these detect and adapt steps, but it gives it, again, this time component that is really, really important here. So let's recap the theoretical foundations of supervised machine learning to then look at the necessary foundation for concept drift detection and adaptation mechanisms. Now, let's say we look at the real world, not at data of the real world, but the real world as it is, with everything that we can observe and that we can't observe. Now, what you typically do is, from this population, you take a bunch of historical data, right? You recall that, typically something like a CSV file or a database, and you have labels of that data. Now you train your model and you try your best to fit your model to your features in order to predict your target, your label target, in this case Y. And the result of that is a machine learning model. What you also did at the beginning is, out of the population, you took test data that you set aside, like we learned, to then test your model. So you apply your model to the unseen data, and then you can compare those to the test labels in the application. The question that we have right now is my population at my new point in time over here, my population dash, still the same as my original population? So is this step of me applying my model to unseen data, like I do in production, is that still meaningful, or do we have essentially different data distributions right now? And to look at that, we have to look at the machine learning model from a data stream perspective, or we also say an online setting where data is frequently coming in. And let's assume for the moment we know that there are two different concepts, concept 1 and concept 2. So we have our incoming data stream, part of it is concept 1, but then after time comes already concept 2. Again, we have our model which has been trained, and the model keeps on making prediction. Now, let's say we adaptively learn over time, right? So you can see we take training data that it might be very old here, not as much as into account as new ones. So over time, my model will update or retrain itself if needed, right? I'm just continuously training my machine learning model, and over time, my predictions will stay valid. And that is a good idea, you might think. Why don't we solve the entire issue like that? Well, because in reality, we do not know which concept a data instance belongs to, right? We do not know necessarily, is this over here a yellow one, or is this over here a gray one? So concept 1 and concept 2. So we need to have a look at the different possibilities that you have at hand. And to do that, we want to look at this 2x2 matrix. The one looks at the model. Is it a single model, or is it a so-called ensemble of models? You might recall this from the random forest that we talked about earlier. So ensemble models are multiple models that make a decision together, and hopefully each of these underlying models has different strengths and weaknesses. So are the models an ensemble or a single method? And how do we deal with updates? With a certain trigger which says now do something, retrain or adapt? Or is it evolving, like you could see in the earlier example where we knew which concept was which? And the result of that are these 4 solution spaces, right? Detectors are single models with triggers. You have the forgetting, which is a single model that is evolving with the data over time. You have ensemble models with triggers, which are the contextual ones. And you have the evolving model updates as ensembles, which we call dynamic ensembles. And let's stick to the example that we just had, and let's look at the forgetting part first. Again, we assume we have 2 different concepts over here, a blue one and a green one. And over time, let's say we have a concept drift. In this case, might be a sudden change or might be a seasonal pattern, but we switch from the blue concept to the green one. Now, let's say we have a fixed training window. So we always take the last X data. That is demonstrated here by this window that you can see. So we always take this and then we predict the next instance. Now, a fixed training window will obviously by design forget about the older concept, the blue one over here. So as our window moves on and moves on and moves on, we slowly forget the old concept and learn the new one. Very simple. You just need a fixed training window for that. Of course, it begs the question on how do you set the window size over here? For which type of concept drift is that meaningful? And that's something that we can discuss in class when we get the chance, right? So I'm not making judgment about the necessarily the quality of these drift detection and adaptation mechanisms, but I will say that this is a very, very easy one. You just have to decide on the window and have to think about for what type of concept drift is that really, really helpful. Okay, I think that's easy. There are also things like weighted forgetting, where older instances are less used. So you could say that there's like still a tiny window potentially over here. It is possible, but again, in general, it looks like this. So let's have a look at a different case. Now we're not evolving, but we have explicit triggers that tell us when to adapt or retrain our model. So same case as before. You can see we have the old concept in blue, we have the new one in green. And the idea is now that we detect this change over here. As a result, drop the old data and then retrain the model. This is obviously something that is good for sudden drifts. Again, let's discuss in class where this might not be helpful. And of course, it assumes that we are good at actually detecting that drift over here and not detecting noise. And that it is meaningful, again, relating back to the problem statement, I think I keep repeating myself. Is it meaningful to drop the old data here in the first place? Or is there still something in there that might also be helpful to the new model? But that's the general idea of a single model with triggers. How these triggers work, how this detection of changes works, we'll have a look at precise algorithms in a second. Now, let's move from the single model to the ensemble. And again, let's start with the evolving case again. In the case of dynamic ensembles, we consider several machine learning models in parallel, so several classifiers. And they look at different samples in our data. So we might have one classifier looking at rather old data in this case, one classifier looking at a mixture of old and new data, another classifier looking at this subsample, and so on. Potentially with different window sizes and with different cases. By the way, we'll go deeper into ensembles in the next lecture, but I think it's already helpful to cover this a little bit here. Now, what we need to do, obviously, is to weigh each classifier and typically do this in a dynamic manner. So that means, let's say we have a binary classification case. We want to classify again as a part within quality or out of quality. So all of these classifiers over here will give a prediction on this specific binary issue. And now what we have to do is we have to combine them somehow into a single prediction with a meta model, right? A machine learning model sitting on top of all these classifiers, or with simple voting, right? And let's assume that we know the true label is in fact plus, so positive in this case. Now we know what the predictions are of all our models, and if I have a dynamic ensemble, it will learn over time in which cases, which of my classifiers is doing a good job. So it could reward those classifiers that are typically correct and increase their weight in my voting, and it could punish those where they were incorrect. And by that, it might hopefully capture over time concept drifts very, very well, right? But you see, you need this extra layer of multiple classifiers and then again a voting mechanism or a meta model which punishes or rewards these underlying classifiers. And again, this is computational intense. Think about the challenges that we talked about again, right? I have to react quickly typically. This does not necessarily always work when I have complex ensemble models. Now, the last class that we want to talk about are contextual models. So the combination of an ensemble method with triggers. And the logic here is still similar to the earlier case. Now we also have multiple classifiers, but they don't all vote at once. But you partition your training data into several groups and then build separate models that are hopefully representative for each of these groups. And that means when a new instance is now incoming, you have some kind of decision mechanism, typically automated, of course, which assigns this new instance to one of those groups, and the corresponding model is applied and gives you a prediction, right? So you have to decide which group does this new instance that's incoming belong to, and then select the model that is appropriate. And that is especially useful for reoccurring concepts, right? Like, again, seasonal patterns in sales forecasts, ice cream sales, and so on, right? If you are very, very sure that you clustered your groups and your corresponding classifiers well, then this makes a lot of sense. And of course, your mechanism in assigning those instances to these groups have to work well. But given that is the case, that is very useful here. And you see the difference to the earlier case, right? Earlier in the dynamic ensemble, we had all the ensembles voting at the same time, looking at different subsamples. But in here, only one model votes. You just have to make the decision first to which model you assign your new instance. Okay, so that was a very quick overview, but now you have an understanding on how can you deal with concept drift. And we talked about these triggers over here. So now we want to look deeper into how do these triggers work. So what are examples for concept drift detection algorithms? And specifically, I want to talk to you today about two of these options. And to introduce the correct terms here, we should talk about so-called informed methods. So these are detector-based methods, and they detect an explicit change and then adapt the model. So these typically work on prediction errors like a sequential analysis like Page-Hinckley, or monitoring two distributions of sliding windows like Edwin. And again, they stand in contrast to the blind methods, these forgetting-based methods, which just adapt incrementally or are frequently retrained. And I want to take a deeper look now at the informed methods, because if you recall the architecture of machine learning operations, having a precise monitoring and then detection of changes is vital for accurate models. So in many cases nowadays, MLOps will be initiated with these detector methods, as you can see on the left here, which is why we want to go deeper into those informed methods or detector-based methods. And there are two examples on how these detections can work. The one is the data distribution-based drift detection. This one tries to quantify any type of dissimilarity between distributions of old data and new data, of course, given the assumption that you're good at distinguishing between old data and new data, and then in the end distinguishing between the concepts that you are trying to detect. Now, the other way to do that are error-based drift detection methods. So they detect changes by considering the error rate of the underlying machine learning model. So basically speaking, does the model make more errors over time? Does the performance somehow decrease? Whereas in the other case of the data distribution ones, we look at the pure data distribution. We do not know how our model necessarily performs, either because we receive the true labels later, we do not know what the ground truth is, right? So you can see that these are two different ways on how to approach the detection. To name a few examples, so especially in the data distribution ones, and these metrics are very old, things like Kullback-Leibler divergence or Kolmogorov-Smirnov, these are all statistical methods or metrics, to be more precise, that allow you to measure distances in data distributions. And then the assumption is that these differences correspond to a different concept. When we talk about error-based drift detection, we look at, there are two main algorithms here, Edwin and Page-Hinckley, one of which we'll talk about in detail in a second. What do those mean for practice? Well, the left one, so data distribution-based drift detection methods, they are kind of a consistency check for your input data. They can check things like the mean, like the variance in the data. The right ones, the error rate based ones, they are often used for a monitoring, a supervision you could call, of the quality and the impact on KPIs. But you also need those very KPIs to use them. The disadvantages of both of these should be mentioned as well. So the data distribution ones, especially if we talk about very high dimensional data, they're computationally very intense. And the error rate based ones, they require, again, true labels for this drift detection. And we now want to look at two of them, on the consistency checks for the input data and also on Edwin as a concept here. And let's start with the consistency check, so a data distribution based drift detection. Now, the idea here is based on a cost function that jumps whenever you have changes or significant changes in your distribution characteristic. Again, we're in the area of data distribution based methods, and what we use here is a sliding window again. Recall the definition of concept drift, different concepts in two different points in time, and the sliding window now moves through this time. And we have a cost function that identifies changes in the signal. The signal is the new incoming data. And the standard deviation can then detect changes in the mean of this signal rising when it jumps. And there are two different cases that we can distinguish into. In both of them, we have this sliding window. And if you exceed a certain threshold in the cost, that means we have a change in the data distribution. So you can see the signals in here, which are the blue dots. And you can see how the mean of the sliding window is calculated and how these costs change. and how it detects this jump over here. And if it exceeds this threshold in the standard deviation, that's the change point that is being detected here. So you can do this by a single sliding window, or you can do it, and this single sliding window is compared against this fixed threshold. Or instead of having this fixed threshold, you can also compare two simultaneously sliding windows. That would be approach B here. So you compare the costs of these two, and you can see in the figure down here, two moving windows, one red and one yellow, and now you compare these change points by both of them. And again, this is very powerful if you only have the data distribution by itself to compare. But what we also have to at least note as a limitation here is now that is a great and easy example, but it's a two-dimensional one, right? One dependent, one independent variable. And one being simply the time over here, and we have one value that changes. So in reality, you typically deal with high-dimensional problems, and those are cases where this might become computationally very intensive. Now, that was a candidate for the data distribution-based ones. Let's also have a look at the error-based drift detection. And one of the most common, most popular algorithms here is the adaptive sliding window, or short ADWIN algorithm. You can already hear from the name that it's about two main things. One, it's about adaptability, adaptive, and then about the sliding window again. And we'll go through the algorithm step by step, but originally it was designed to automatically adapt to changing patterns in the data, and concept drift detection in machine learning is a great case to do that. How does it work in general? Well, we have a detection window called W, and that iteratively adapts. And we typically look at two sub-windows of W, and if we can exhibit distinct enough means in those, the algorithm will drop older elements, right? So we have a sub-window that gets larger, but once we detect a significant change, we will reduce the window. And the threshold for that is defined by the epsilon cut over here, by the Höfting bound. That is a statistical tool, you could say, to determine confidence intervals for the mean of a random variable. And these bounds provide a way to estimate how much a sample mean deviates from the true mean of the underlying distribution with a high confidence. And this is really, really useful for these data streaming, for these online settings, where you want to detect exactly those changes. And in theory, ADWIN works really, really well with different types of changes, like incremental changes and sudden changes. If that's always the case, that's something that we can discuss in class and that we can try out in the exercise. But in general, it should be applicable to a bunch of different concept drift types. Now, let's go through the algorithm step by step in the next, on the next slide here. And we'll have a look at that from a sudden change perspective, right? So we start with a window over there that you can see. So first step is line 1. Let's go through it line by line. Line 1, initialize the window W. So this initializes an empty window W that will be used to store the most recent observations in the data stream. Again, this is the data stream, and the blue points over here are the observations. So this is W, and now let's move to the second line. For each t larger than 0, and this is a simple loop, right? This starts a loop that processes each new data point xt now as it arrives, the lighter blue ones that you can see up there. And now what it does in this iterative loop over here, we are now, let's move to line 3. Now in this step, we add a new data point xt to the window W, keeping it at the front or the head of the window, and thus maintaining the most recent observation in this window W. And what we do now in the fourth step over here is we repeat dropping elements from the tail of W. So the loop continues to drop the oldest data points from the tail, or the end of W here, one by one, to make sure this window size is adaptable. That's where the name comes from. And the goal is to shrink the window if a significant change is detected between the newer and the older parts of the window. And that's where we have to go into line 5 over here. So what that does, and you can see the neat animation. So in line 5, W is split into two parts. W0, and that is the older part, and W1, that is the newer part. And now the algorithm calculates the absolute difference between the means of these two parts. So the mean between W0 and W1. And if this difference is greater or equal to a predefined threshold, epsilon cut, this indicates a significant change between the older and more recent data in W, suggesting that in fact we experienced a shift. Now, of course, you ask, where does this epsilon cut come from? This is a parameter that we need to set, and this determines also how sensitive Edwin is to changes. And of course, this can be debated how you select it. But anyway, let's take that as a given now. And so whenever this happens, whenever we do detect a change, which has not happened here yet, W would simply grow. But for every split that we would now do for W, that's this part over here. So W is split into W0 and W1, so the older and the newer part. W0 will be removed from W. So that's the case where we receive a new updated one over here. So the algorithm outputs the mean mu W of the current window W, which now contains only the most recent observations after potentially discarding the old data, right? So by that, step by step, this window gets adapted, and if we have a significant difference between our W0 and W1, that is now where we come to line 5 and 6 of the algorithm and apply this cut, right? So that's neatly explained for how it works for sudden changes, and it works very well there. The question is, how does it behave in other cases like slow changes? And that's something that we will try out in the exercise. The last thing I want to do now is dive into real-world examples for concept drift handling. And there are obviously a bunch of those, because as we discussed, there are many challenges when it comes to the validity of machine learning microservices. So the typical issues that you have can be categorized into 3 different types, because various threats exist for this validity of the microservices, and we discussed them already, right? The first one being, again, the difference between deployment environment and development environment. Again, during development, you often assume things. Models are trained on well-defined, curated data sets without any noise, without any label errors. And then in deployment, you see that the data input shows great variance, and typically things like we discussed in the initiation section, noise, missing labels, things like that. And a typical example for that are outliers in input data during deployment. Suddenly you find out that there are way more outliers than you experienced in your development. Maybe because you excluded these for developing your model, but now again in the real world, you are confronted with them again. The second one is the environment of the microservice. So changes in the environment. Let's say simple things. You move a machine to a different part of your production line, or you exchange the machine, or your sensor, again, wears out over time, becomes rusty. This is a big issue, right? Whenever you change that environment, your model will be confused. And then this change can be due to many reasons, but one of the most interesting ones is you do change the environment actually because of applying that very microservice, right? So the application of the service affects the prediction quality. I mean, hopefully you did that to improve the overall quality of what you were producing, building, trying to do. But then again, your model only learned the patterns from your original set. And a great example for that, well, there are two. One of them my colleague did is in continuous predictive policing. So what you do in predictive policing is you try to identify where is the probability of a crime very high, at what time of the day, which parts of the city, who might commit them. But the reason for doing that in the first place is, of course, not to sit still and simply monitor where crime will be happening and can happen, but you will send out police force to those areas at those times. And this will have an impact, obviously, on the environment. But this affects your very model because it worked on different assumptions about those different regions. Now, if you send more police force in there, this will change. So continuous predictive policing service is a great example for how you want action to be taken, but this action again influences your original environment and you need to adapt your service. Or different case, behavior of people in online settings, right? Like clickstream optimization. Let's say everything you hope for works out in your machine learning model and the people take the action that you want them to do. This obviously changed their behavior because now they start clicking on the ads that you wanted to, but are they then still the same people that you wanted to target in the first place, or do you need to change something here, right? So these are three very, very typical threats when it comes to the validity of these machine learning microservices, and that's why we need concept drift, detection, and adaptation. There are a bunch of studies, of course, that have been performed on concept drift in various domains. So, for example, in monitoring and control, where you do real-time monitoring. For example, for chemical production, you have things like robots playing soccer, anomaly detection when it comes to networks. Now, all of these cases are about very, very fast concept drifts where you have to adapt really, really quickly again. And there we come to also hardware limitations and computational limitations. But moving away from that, looking at information management, there you typically have timestamp data where you have sudden or gradual concept drift. So in personal assistance, like categorizing news, spam filtering, both news and spam will change over time. Marketing, customer segmentation for cars recommender systems, right? The car sector is changing, the customer is changing, the requirements are changing all the time. Or also when you come to management, it's about archiving of documents and the type of documents that are of interest here. And then finally, something that is very close to us, obviously, is the whole area of analytics and diagnostics, which is also deals with a lot of timestamp data. And typically you observe lower or slower concept drifts over here, right? Like population drifts. This applies to forecasting, like macroeconomic forecasts. How much revenue will the state make? How many taxes can we expect? Medicine, antibiotic resistance, also over time. Security, how can you use biometrics here, right? You can see, so there are many, many, many cases where people have performed studies on these various application forms of concept drift. However, I want to dive deeper into one of the examples that we've been working on in the past, which is the New York taxi demand. If you're interested in cases of sudden drift, a bunch of things might be worth looking at, right? You could look at temperature levels in different countries and different regions, stock prices, taxi demand, and demand for groceries. And as I said, we looked at taxi demand as an interesting case, more specifically on the so-called New York City taxi data set, which is very, very common. You can see a distribution on the data over here. geographically, by region. What does this data set consist? It has 1.4 billion rides of yellow cabs. By the way, it's still recorded up to today, but the one that is very frequently used is the time span between 2009 and 2018. And this set includes a bunch of information, like where were people picked up, where were they dropped off, what fare did they select, how much tip did they give. And of course, you need various pre-processing steps, again, to make this digestible. And what we want to do is we want to predict the hourly taxi demand per taxi zone. So there are these different zones that you can see up here, and you can see in how large the problem becomes there. But it's not only a good case for sudden drift, but as we will see also for other types of concept drifts. So let's have a look at that. Let's first have a look at the timeline from 2009 to 2018 and the number of rides for the different types of pickup services that you can choose there. So you can see the traditional yellow cabs, you can see Uber and Lyft. And one of the things that is, I think, obviously notable is how with the rise of both Uber and Lyft in New York City, the traditional yellow cabs went down. You can also see the amount of total rides, which in fact went up, which is interesting. So this is a great case for an incremental drift. So again, decreasing demand for yellow cabs over time because new competitors came to the market. Second example, let's look at a specific day. In this case, it was the 27th of January 2015. And you can see how the pattern is kind of unusual. So you have the average demand for a Tuesday like that, and now you have the precise demand in blue here and compared to this. So something was definitely different here, and that was a very unusual demand for Tuesday because, in fact, that was the time of an extreme weather phenomenon. In this case, January, New York City, it was a blizzard. And we can also see seasonal changes on this very chart here, right? Especially things like New Year's Eve, yeah, right? Very different behavior of people there on public holidays. So that's why you have all the interesting drifts in the taxi data set, and it's interesting to look at. We were pretty much inspired by these ensemble methods in how to deal with concept drift. So we came up with a new idea, which we labeled as the error intersection approach. And it's interesting because we built it to be functional and not too resource intense. So we initiate both a simple model and a complex model. And now you have an incoming data stream, and the model switches between these two models. So in case of a sudden drift, it would go and use the simple model, whereas the complex model would be used for ordinary days. And now you can switch between both of those. So the simple model needs to quickly adapt to changing circumstances. So in case there is a blizzard again, or we have New Year's Eve, then we would use such the simple model. And the complex model, as you can see, deep neural network over here, right, with multiple layers and two different activation functions, would work as the complex model. And without going into detail, now we designed the algorithm in a way that it intelligently switches between those models, because one of the typical drawbacks is that you have to react in real time. And once you detect a drift, calculating now a new model is way too complex. And we applied this to the data set and could find out where drifts were detected. And in many cases, we could pinpoint a semantic reason for that, right? So our model is very accurate in detecting 4th of July, for example, Hurricane Sandy, Christmas Day, that blizzard that I talked about, cyclones. But we also find evidence for days where we cannot explain the drift cause, right? And that's one of the toughest things in concept drift. And maybe that's like my final message here is it's so hard to find the real influencing factors. And also like the causal influence factors behind that. In hindsight, it's sometimes easy. You could look at the data and say, oh yes, there was a blizzard. Oh, that was Christmas Day. but they might not be obvious in real time. And that is so tough, because the hindsight analysis is always easy, but in concept drift detection adaptation, you have to work in real time. You have, in best case, you understand the influencing factors and adapt in the best possible way. So let's quickly summarize what we learned today. First of all, it's really important to continuously monitor your deployed machine learning solution, because your environments do change over time. We discussed a bunch of different challenges, but that's something that will typically happen. And not only on the floor of a production facility, but nearly in all application domains, which is the second point here, right? So that's why a paradigm like machine learning operations already considers concept drift as a very, very important aspect. If you decide to do something about it, then of course you have different adaptation options. We talked about that, right? Do you want a simple model, a complex model? How is the ensemble look like? Do you want an evolving or a triggered solution? And again, bunch of options that you have at hand here. But those choices must be made when you implement the model, and also typically not afterwards, but while you develop the model, you have to think about that. And then again, it's really hard to say which of these detection and adaptation mechanisms works best for what type of use case, because in many cases you also simply do not know what types of drifts to expect. I mean, if you would know, that would make things easier. So it's a lot of trial and error, and typically it also involves, in the end, humans to check on these concept drifts, which is, I think, a great transition to the human AI collaboration lecture that we will have later. Okay, so thank you very much for attending this lecture. Again, last time that we are within one AI, but we covered now this entire cycle, and now I'm excited to move into the next stage where we talk about AI in systems. Thanks so much for watching.